So conservation of angular momentum says that when two conditions like this is a string and this is an object, mass of m, the distance of is separation from the point of rotation O is equal to r1. So okay, and it was rotating with velocity omega 1. So suddenly imagine I am standing on here and I suddenly reduce the rope, reduce the string to a distance to r2. It is rotated like this. Okay, so r2. Okay, suddenly I reduce the distance to r2 by pulling, and so it will rotate with the angular velocity of omega 2. Mass is still same. So the conservation of angular momentum says that the angular momentum of first case is equal to the angular momentum of second case. L1 is equal to L2. It implies r1 square omega 1 is equal to m r2 square omega 2. This is the conservation of angular momentum. That is a simple proof of conservation of angular momentum, but today I am here going to uh, find this expression using conservation of. Consider me as the yellow person. I am holding a mass. I am in the thread, and I am rotating with the velocity omega, and the distance of separation is r. So I am rotating the object parallel to the xz plane. I have shown the coordinate system. I think you have understood how I am rotating. Then I simply draw the coordinate system to know how I am rotating. Then sudden and this mass has a centrifugal force which is acting towards like this. The centrifugal force F is equal to m mv square by r. I can write it as mr omega square. Okay, F is equal to mr omega square. So mr omega square is acting outwards. So assume I pull the string. Through a distance dr like this. I have pulled inward to the distance dr as shown like this. Dr. I have pulled inwards. So dw is the work done which take me to pull the string. dw is equal to f dot dx. I simply wrote the general equation, and f dot dx is the dot product. So dw is equal to f into displacement is dr into cos theta. Here the direction of force is f here, and the direction of object which I have moved is through like this here in this direction. So the angle between here theta is equal to 180 degree. So cos 180 degree which is equal to -1. So I will write it as dw is equal to minus f into dr. W looks like angular momentum. I will write properly W. So dW is equal to minus m r omega square into dr. Equation 1. So here I can take in two cases, case 1 and case 2. Case 2 1 is the usually it is rotating with the radius r. Case 2 is when I try to pull, so the radius reduces to r minus dr. Case 2. Okay, so let us find the kinetic energy of case 1. So again write as k1. K1 is equal to half v square. V square is half m r square omega square. K1. K2 I can take it as half m r plus delta r omega plus delta omega square. So K2 I can write it as half m r plus dr omega plus d omega square. So K2 is equal to half into m r omega plus omega dr plus r d omega plus dr d omega square. So this dr d omega can be reduced. So K2 I write here another color. K2 is equal to half into m into r omega plus omega dr plus r d omega. So I can also write as K2 is equal to half into m square omega square into dr by r plus d omega plus 1. So changing kinetic energy. So when I do this work, so the kinetic energy will be increased. The work will be utilized, will be changed to the kinetic energy, and the kinetic energy will be increased. So the kinetic energy, increase in kinetic energy. Increase in kinetic energy is equal to K2 minus K1, which is equal to half m square omega square into 1 plus dr by r plus d omega by omega minus half m square omega square. This square, okay. Okay, let dr by r plus d omega by omega is equal to a, and q is equal to half m square omega square. So delta k I can write it as q into wait 1 plus a square, sorry, let's say the whole square minus 1. So delta k I can also write as q into 1 plus a square minus 1 square I can write as. So a square minus b square format. So that I can write as a into a plus 2. Delta k is equal to q into a square plus 2a. So here we can observe that a is equal to dr by r plus d omega by omega. So if we square this 2, it will be very small. So this a square can be neglected. Delta k is equal to 2qa into q into a. So this increasing kinetic energy is equal to the work which I have done, 0 dw. So increasing kinetic energy 2 into q into a is equal to work done, dw. So this q is equal to 2 into half into what is this q, m r square omega square. Okay, m square omega square into a is equal to dw. dw is equal to minus m bar omega square dr. Minus m bar omega square into dr. So this 2 and 2 will be cancelled. This m will be cancelled. R and R cancel. Omega square cancel. So can write as minus dr by r is equal to a. P can be replaced as dr by r plus d omega by omega. So when you cross multiply, minus 2 dr by r is equal to d omega by omega. So integration. So r1, r2. So when corresponding angular velocity of r1 is omega 1. Corresponding angular velocity of r2 is omega 2. So you can write it as minus 2 ln. When I am integrating it, I can write it as 2 ln r1 by r2 is equal to ln omega 1 by omega 2. So we can write this r2 by r1 the whole square is equal to omega 1 by omega 2. So rearranging, here write this omega 1 r1 square is equal to omega 2 r2 square. So when I am multiplying here by both sides by m, I can write m omega 1 r1 square is m omega 2 r2 square. M omega 1 r1 square is the angular velocity of case 1 is equal to m omega 2 r2 square is equal to angular velocity of case 2. So L1 is equal to 2. This is the conservation of angular momentum. This is the proof.